work on symplectic embeddings. This is joint work with Daniele Sepe. So I'm going to start by introducing the subject. I think most of you here know about the famous theorem of Gromov, but let me just start with that. So the question that we have in general is, when does one symplectic manifold embed into another? So that means when there exists a smooth embedding of M1 into M2, which preserves the symplectic form, or in other words, the pullback of omega 2 is omega 1. So that's the general question. And the first answer to this question was given by Gromov in a very famous theorem. So if we call B2n of R, this is the set of points in Cn such that pi times the norm squared is less than or equal to R, then Gromov said that B2n of R symplectically embeds into B2 of R cross Cn minus 1 if and only if the radius of the big ball is less than or equal to the radius of the cylinder. So I'm going to say this once and for all. All the domains I'm going to pick here are subsets of R2n, and they're going to be given with the standard symplectic form. So the symplectic form is always going to be dxi dyi in Cn, which is R2n. So this was the first theorem in this field, and it was pretty revolutionary because it's also where he introduced J-holomorphic curves in the study of symplectic geometry. So, this was in 1985, so a lot of things have happened since then. So the first, and the next result I want to tell you about is about embedding ellipsoids of 4 dimensions. So in 4 dimensions, we could define an ellipsoid with parameters a and b. So this is the set of z1, z2, and c2, such that pi norm of z1 squared over a plus norm of z2 squared over b is less than or equal to 1. Actually, let's do less. Let's do the open ellipsoid. And you can see that you actually only need 2 parameters to define the general ellipsoid in dimension 4, because up to a symplectomorphism, we can make 2 of them the same. Okay, so then McDuff proved in 2009 that an ellipsoid with parameters a, b symplectically embeds into an ellipsoid of parameters a prime, b prime, if and only if a number theoretic condition on a, b, a prime, and b prime is satisfied. Okay, so I won't tell you what it is, but it's a pretty simple number theoretic condition on these 4 numbers. And you should think that that's quite amazing, because in general, it's quite difficult to say when symplectic embeddings exist or when they don't exist. And before I keep going, let me just tell you there are 2 sides of the story. There is sort of the constructive or the optimistic side, and then there's the obstructive or the pessimistic side. So basically, Gromov showed that if you can include this domain into this domain, then basically that's the only thing you can do. So Gromov's result, in some ways, is an obstructive result. Like, you can't do anything better than the inclusion. And over the course of the time, people also created or were able to construct non-trivial symplectic embeddings to show, basically, to improve the construction. Say, actually, you can do things that are a little bit more obvious. A little bit less obvious. And basically, you have a theorem when these two kind of converge. When you say that you have a nice theorem like this, when you say that the obstruction and the construction kind of coincide. And I think this is a really, really beautiful one because in this case, both directions are highly non-trivial. So the obstruction is far from being something obvious. Actually, it can be encoded in terms of embedded contact homology. But the construction is also highly non-trivial. It uses the Seiberg-Witten invariant in dimension 4 and a few other things. So what is this number theoretic condition? So this is, in this case, it's encoded by what are called embedded contact homology capacities. So Dan talked a little bit about embedded contact homology before. I'm not going to say very much about it, but I just want to say that there are these things called ECH capacities, which are the following. So given a four-dimensional symplectic manifold, you can construct a sequence C0, C1, etc. So it's an increasing sequence or a non-decreasing sequence, and they could maybe be infinite at some point, but usually they're not. And the number theoretic condition that I mentioned is that the CK of EAB is less than or equal to the CK of EA prime B prime for every K. Okay, so these numbers can be computed. So this is due to Michael Hutchings. These numbers can be computed. They're pretty easy. They're just integer combinations of A and B. Okay, so this theorem was generalized by Dan in a very nice way. So Christopher Gardner basically said the following. Actually, you don't need to only consider ellipsoids. You could consider domains that are a lot more general. So we have these things called toric domains. So let's recall what toric domain is. So if you have a region in the first quadrant of R2, you can consider the set of points in Z1, Z2, and C2 such that basically the norm of Z1 squared and the norm of Z2 squared times pi belongs to omega. I mean, this pi here is just a normalizing constant, so don't worry about it. In other words, if you know about Hamiltonian toric actions, this manifold admits, this is a subset of C2, and the standard Hamiltonian toric action on C2 preserves this set. And this set, omega, is the moment map image of X omega. Okay, so this is a pretty standard way and to construct manifolds, symplectic manifolds. And like this, you can generate a very large family of interesting things. And there are two specific kinds of toric domains that are particularly nice. So there are the called concave toric domains and convex toric domains. So a concave toric domain is one of that form whose moment map image is something like this. So it's a region that's bounded by the two axes and the graph of a convex function. And a convex toric domain is the same thing, but the graph of a concave function. Okay, so what Dan proved is that basically Dusa's techniques can be adapted to the case of when you're trying to embed a concave toric domain into a convex toric domain. So Dan showed that a concave toric domain symplectically embeds into a convex toric domain if and only if the ECH capacities of this guy, the ECH capacities don't give an obstruction. So if and only if the ECH capacities of this guy are less than or equal to the ECH capacities of this guy. So of the concave to the convex for every k. And again, the technique is very similar, and there is the obstruction side, which is the ECH capacitors, which is pretty, it's a big black box, and the constructive side, which also uses, the Seiberg-Witten invariant and a bunch of things. So neither direction is very, very easy. But it's still, it's a very nice theorem, and it answers the questions of symplectic embeddings for a lot of toric domains. Now you could ask maybe, what about the other direction? Or what about embedding things that are convex into convex or concave into concave? The question becomes a lot harder. And one of the big challenges is that constructive methods become very difficult if you're not trying to embed a concave into a convex. But if for some reason you have other tools, and you could still use all the capacities that you know, and Michael developed these other methods that use more refined information on ECH in a paper called Beyond ECH Capacities that come up with more obstructions. But basically, there are no revolutionary constructive methods, as far as I know, in other situations. But what I would like to tell you about today is a different kind of domain. So a couple of years ago, I started thinking about a domain that is not toric as a starter. So one other kind of domain you can look at is a disk bundle. So one of the most classic examples of a symplectic manifold is the cotangent bundle. So if you look, if you're looking for a compact thing, you can look at the disk bundle of a compact manifold. So let's look at the disk bundle of D2. So the disk bundle of D2, you can think of it as just being, the set of P and Q in the cotangent bundle of R2, such that the norm of P is less than 1 and the norm of Q is less than 1. Okay. So you can ask about the symplectic geometry of this set. This can also be called the Lagrangian product. So this is what's called the Lagrangian product of two disks. So you have the product of two disks, but Lagrangian in the sense that each disk by itself is a Lagrangian submanifold. Okay. So you can ask about questions related to this set. And the theorem that I proved in 2015 is that this guy embeds into the ellipsoid if and only if the smallest parameter is at least 4 and the largest parameter is at least 3 square root of 3. Okay, these numbers seem a little random, but I just want to emphasize that these numbers, there is no other way to tell these things. And yeah. And the other part that I showed that is basically a consequence of this is that if you're trying to embed it into a ball, so a ball parameter C is an ellipsoid with parameter CC, this exists if and only if C is greater than or equal to 3 square root of 3. There are some reasons that I'll explain later why these numbers are not completely random. And, basically, I started working on this because I was asked a question by Felix Schlenk, and he wanted me to show that the best embedding would be, of the bidisk into a ball, would be when C is greater than or equal to 4 square root of 2. But this is actually better. So 3 square root of 3 is better than 4 square root of 2. And in a little bit, it will become clear why these numbers are not completely random. Okay. So now we can say, well, you took the Lagrangian product of two regions in R2. What can you say about taking Lagrangian products of, two different regions in Rn? That's a huge source of examples that, as far as I know, have not been investigated very much. So let's just talk about the Lagrangian product in general. So say that you have A and B subsets of Rn. You can take the Lagrangian product of A and B. So this is the set of x, y in R2n such that x is in A and y is in B. And the symplectic form is dxi dyi. Okay? So, well, why do we care about these domains? Well, first, it's a big source of domains. It has nothing to do with being toric. But, you know, let's see what we can say. But there's another reason why we care about this domain, which is related to the billiards. So let me try to explain that give you some motivation before I start telling you about the results. So why do we care about these domains? So let's assume that A and B are convex for simplicity. So the idea is that if you have if they're both convex, the product will be a convex, not convex toric domain, but just a convex set in R2n. And the symplectic geometry of a set like that is pretty much determined by the boundary. So the idea is that the symplectic geometry of this manifold is related, or basically pretty much determined by the contact geometry of the boundary. So what do I mean by contact geometry of the boundary? Well, you can take the radial vector field, and then when you restrict that to the boundary, that will give you a contact form on the boundary. So if you understand that contact form on this 2n minus 1 dimensional manifold, then you basically understand the symplectic geometry of the whole domain. So let's see, for example, that maybe the most important thing we would want to know is about the Rabe orbits. Or in other words, you don't even have to talk about contact geometry. You can just talk about the characteristic vector field. So that's the kernel of the symplectic form on the boundary. So we want to look at what's called the characteristic vector field on the boundary. And this is where things start to get interesting. So basically, I'm going to draw the picture in 2 dimensions, because that's all that I have on the blackboard. But you can picture the same thing is true in higher dimensions. So if this is A and this is B, so when you're on the boundary, then basically there are 3 different parts of the boundary. So you have sort of the interior of A times the boundary of B. You have the boundary of A times the interior of B. And then you have the boundary of both. Okay. So let's look at each of these 3 parts, basically. So this is just a small calculation. So the characteristic vector field is a vector field in the line bundle, which is the kernel of omega. So this belongs to the kernel of the symplectic form on the boundary. Okay, so this is not very hard, because basically, so you look at the kernel and you can do a little calculation and see that what happens is, let me write the 2 pieces, is that here you're going to be moving the A in the A direction, ddx1 plus ddx2, but the vector that you have here is the normal vector at the point y1, y2. Let's see, sorry, normal vector 1, normal vector 2 with respect to y. So what does that mean with a minus sign in front? That means that if we're in this part, then I'm in the interior of A and in the boundary of B, somewhere, I don't know, here. Then I'm going to be moving in the direction of the normal vector field here, but I'm going to be moving this guy. Okay? So and then here you have something very similar. You have ddyi plus ddy1 plus ddy2, and then the normal at x, coordinates 1 and 2. And of course, this generalizes to higher dimensions too. So basically, depending on whether you are here or you're here, if you're trying to follow the characteristic flow, you follow this vector field or this vector field. Okay? So you can...
I don't understand. How can you be pointing outward? Are you getting out of the domain?
Oh, no, you're not pointing outward. What I'm saying is that you are at this point and at this point. So, I mean, you're at this point, comma, this point. So the vector field that you have is, you look at the normal vector field over here, and then you use those coordinates, and you plug them with the ddx1, ddx2. And you have a minus sign. Yeah, and this component, and in this component, you don't have a minus sign. That's just an orientation thing. But, like, say, for example, you are, okay, let's do an example so that it's kind of clear what I'm talking about. So say that you are at this point here and at this point here. So you're in the interior of B and you're in the boundary of A. So what you're supposed to do is you're supposed to use the normal vector field here and flow this guy in that direction. So you go all the way till you hit the boundary. So when you hit the boundary, basically now you go to the other guy. So now you basically have to start moving in over here in the interior of A with the direction given by minus the normal of B at B. So now you move basically like this. And then all the way till you hit the boundary again. And then now you hit the boundary, and then you go back here, and you go like this. And then this is how the characteristic flow is given. Okay? And the interesting thing that you can see now is that if A and B are actual circles, then basically this angle, well, actually this angle is always equal to this angle. And this angle is this angle. So this is just very basic geometry. If both of them are disks, then this is what you get, which means that, sorry, this is the center of the disk. Which means because these two angles are the same, these two reflection angles are the same. So if you have a bidisk, then what you're seeing here is actually a classical billiard on a circle. If the geometry, if these guys are not disks, then of course these angles are not the same, but somehow these angles are determined by the geometry of this guy. So basically this is what we can call, this is billiards in B with the geometry of A. And kind of vice versa too. If you just look at this side, you're going to have billiards in A with the geometry of B. So that's basically why billiards come into the picture. Because the characteristic flow is basically given by the billiard flow. Okay? So that's one of the reasons why we're interested in these domains. I guess I should say one more thing before I state the main result, which is the main technique to prove this theorem here is to actually notice that this bidisk turns out to be a toric domain. So using this description of billiards, I was able to construct a Hamiltonian toric action here, which is not kind of the obvious action. The obvious action doesn't preserve this domain. But there's another kind of hidden action that uses the billiards, which does. And so basically the other theorem that was necessary for that is that this bidisk is actually symplectomorphic to a toric domain. And the moment map image is actually something concave. So it's symplectomorphic to a concave toric domain. And I can tell you what this equation is, just for fun. So you know that it's very explicit. So this guy is a curve. It's 2 times cosine of t minus t sine of t, and then cosine of t plus pi minus t sine of t, t between 0 and pi. Oh, sorry, I got sine and cosine confused. So anyway, it doesn't really matter what it is, but you can check, you can draw this curve, and you see that it's actually a concave thing. And then you can, if you remember Dan's theorem, which I just erased, Dan, tells us how to prove, or how to work with symplectic embeddings of concave toric domains into convex toric domains. And this is exactly the situation that we have. So this is a concave toric domain on the left, and this is a convex toric domain on the right. So basically, then you have to compute a bunch of VCH capacities, which you can do, and then use Dan's theorem to conclude that these embeddings exist. Okay, so that's the end of the theorem from 2015. So now, all this motivation that I gave is also true for higher dimensions. Yeah?
May I ask you, just to understand, so the optimal embedding into the ball and into an ellipsoid, you can't give it explicitly.
No. It uses inflation, the subroot invariant, and all that stuff. Yeah.
If it had been 4 through 2 or whatever, the one Felix originally thought.
Then you can do it explicitly. Yeah. Yeah.
Is it like a fold or an inclusion? I mean, how
Well, you see it in maybe like 10 minutes. It'll be clear what the embedding for forward of 2 is. Yeah. It's not folding. I think it's basically simpler than folding. Yeah. So what I want to tell you about is some recent results that we have with Daniele. So when I gave this talk before, the first thing people asked is, what about a Lagrangian product which is not ball disk times disk? And the problem is if you change it a little bit, then all the techniques that I use to construct this symplectomorphism just break down very quickly. I use the symmetry of both things very strongly. So there's no obvious way to generalize this result to other Lagrangian bidisks. But what I managed to prove with Daniele is that if there's still some symmetry, then we can prove things. So what's the symmetry that we need? Let me tell you that. So we say that A is a subset of Rn, which is open, precompact, and convex. So we say A is symmetric if A is invariant basically under reflections about all the coordinate planes. So it's invariant under taking xi to minus xi. And also when you switch coordinates. So if you do xi, xj, xn into xi, x1, xj, xi, xn. So it's invariant under reflections about the coordinate planes and about all these other directions. Okay. So if it's invariant on this, I say that the domain is symmetric. So a big source of examples of symmetric domains are the P balls, so norm P. So source of examples are the balls in norm P. So this is the set of X in Rn such that the sum of xi to the P to the 1 over P is less than 1. Okay? So we can also talk about the infinity ball, which is the limit of that, or the norm infinity. Okay. So now I can tell you what the theorem is. So the theorem is that, let A be a symmetric domain, and let A prime be a symmetric domain, but that one of two kinds. So I want A prime to be either the 1 ball or the infinity ball. Okay, so this is a cube, and this is kind of a high-dimensional diamond. Okay, so this guy or this guy. Then, if I take the Lagrangian product with the cube, and I try to embed into the Lagrangian product of A prime with the cube, this happens if and only if A is contained in A prime. And also if you do A prime into A. Let me write this, and I'll explain. So this is the family of Lagrangian embeddings that we're looking at. So we're looking at a symmetric, any kind of symmetric domain times a cube. So what we can show is that embedding a symmetric domain times a cube into another symmetric domain times a cube is extremely rigid, provided that one of the two is either the cube or the high-dimensional diamond. Okay? So, so that's the theorem. Any questions about the statement of the theorem? So before I talk about the proof, I want to just mention a pretty corollary of this. So the corollary is the following. Say that you take PQRS numbers 1, 2, or infinity. And say that you want to embed BP times BQ into BR times BS. So no, basically you take a two-dimensional diamond, a circle, and a cube. And now say you wanted to take the product of any two things that you can think about. And I want to know when this embedding problem is rigid. So the corollary is that this is rigid if and only if PQRS are not a very specific kind. So they're not, basically this is always rigid unless PQRS are kind of the bad ones. So it's 1, infinity, 2, 2, infinity, 1, 2, 2, 2, 2, 1, infinity, and 2, 2, infinity, 1. So in other words, take diamond, disk, and square. Take the products of all of these. Take the product of two of these, and then take another product, and try to embed one into the other. So there are only basically two cases that are bad, which are if you try to embed the product of the diamond and the square into the bidisk, and the bidisk into the product of the diamond and the square. So everything else is rigid. And what do I mean by rigid? I didn't quite define rigid. But it basically means that if you're trying to embed this guy into a multiple of this guy, this happens if and only if you have an inclusion, up to the obvious transformation. So the obvious transformations here is flipping these guys and kind of scaling one by a factor and expanding the other by the same factor. So that's an obvious simple ectomorphism. So a problem is rigid if basically you can't do any better than inclusion, apart from these obvious transformations. So what I'm saying is that except for these funny cases, that everything else is rigid. Okay, let me explain why these cases are funny. And these were actually in my previous work. So these cases are funny for the following reason. So proposition, I think this was definitely known by Schlenk in his book, but it could be older. So this is in Schlenk's book from 2005, I think. If you take the diamond Lagrangian product with the square, this is symplectomorphic to a ball of parameter 4. This is a 4-dimensional ball. Okay? So Felix already knew that if you do that, you get the ball. And why is that? Well, this is the following argument. You can construct a family of area-preserving maps that goes like this, basically. So what you want is you want to basically take a disk into a rectangle. And this is 1, and this is -1. So you want to take an area-preserving map that takes each disk to a rectangle of height 2 and some variable width. Of course, you can't do that with a diffeomorphism, but you can almost do it. So what you want is you want sort of psi norm of the second coordinate of psi, no, the first coordinate of psi to be less than or equal to pi norm of z squared over 4. That's what you would get if you can transform a disk into a square of height 2, and a rectangle of height 2 and variable length. So this would have the same area. But you can't exactly do that. It's clearly not going to be a diffeomorphism, so you need a little wobbling space. But you can do it up to epsilon. So this is kind of a variation of, I think, the original argument by Lisa Traynor. And it's very nice, very nicely explained in Felix's book. So basically he says you can construct this area-preserving map, and then if you do it twice, then so if you do phi and then phi again, so from C2 to C2, it turns out that this will map the 4-dimensional ball of radius 4 into, so in the x-coordinate, you're going to have this norm plus the norm of the other guy bounded by something. So that's going to be the diamond. And then the second coordinate, you're going to be between -1 and 1 for both of them. So times the square. So this is a little exercise, something you can check. But if you understand this area-preserving map, it's not very hard to see that you get this. And you have a little wobbling space, too. So you kind of embed this guy into here, and you have to do a little argument to show that the epsilon can be taken to 0, and you actually have a symplectomorphism of the interior into the interior. But this is somewhat classic in the field. So basically, this means that this Lagrangian product is symplectomorphic to a ball. So the bad cases in this corollary are basically 2. So the bad cases are this guy into the bidisk, and the bidisk into the product of the diamond with the square. And let me tell you why these problems are not rigid. So they're not rigid for the following things, for the following reason. We already knew from the paper that I mentioned in 2017, we know that B4 embeds into the bidisk. So this is something that was already known, which means that this guy, with no factors, this guy has to embed into the bidisk. So here, these parameters are all 1. And you basically see that this doesn't fit. So, you see this guy does fit. Let me use colors. So this guy does fit exactly, but this rectangle doesn't fit. And of course, there's no way of shrinking this guy, because if you shrink this guy, then you expand the other guy. So this problem, is not rigid. If you try to do the other way around, and now I'm going to get to the answer of your question, Dan. If you try the other way around, if it was rigid, then the best thing you could do is to put the disk exactly in here and the other one exactly in here. So if you compute if you look at the parameters, that would mean that you're embedding into the ball of parameter 4 square root of 2. But we know, again, by this paper, that you can do better than that. You can actually embed into a ball of 3 square root of 3, which is contained in this guy. Okay? So that means that this is not rigid and this is not rigid either. But basically, any other product is going to be rigid. Okay. Any questions about this? So why did I pick such products? So why did I pick a product of a symmetric set with a cube? So what I would like to do now is to explain, so why symmetric times cube? Okay, so this is because these guys turn out to be our friends, the toric domains. So the theorem is that these guys are symplectomorphic to a toric domain. And how do you obtain this omega from A? So what you do, so remember for the ball, so what was the 4-dimensional ball? The 4-dimensional ball, I explained that if you take the diamond times the square, this is symplectomorphic to a ball, which in the moment map image is this guy, toric. And if the parameter here is 1 and 1, then here we get 4. So what we proved is that this omega here is basically, you take your symmetric domain A, and you just take the first quadrant or octant, or the higher dimensional version of that, the 2 to the nth region, and then you just expand that. So this omega is the set of x1, xn in Rn greater than 0, such that 1/4 of this belongs to A. Okay, so if you have symmetric times cube, this is going to be symplectomorphic to the toric domain that has the same shape, so 1/4 of this, but with 4 times the parameter. And it's pretty easy to check that these have the same area, or the same volume. Sure, yeah. It's the same, yeah. You can switch the factors, yeah. There's no problem. So how do we prove this theorem? So here's where you have to use integrable systems. So the proof, we use integrable systems. So how do we do that? Well, basically, first you start with Rn times, you can kind of do it all at once for all the symmetric domains at once. So you, actually, no, let's just do it like this. So you can consider the following system. You can do 1 over 1/2 x1 squared, 1/2 xn squared. So that will give you a map into Rn. And this system is integrable. And what's amazing here is that these variables are all these variables are independent. So basically, and that's because we're taking the product with the cube. So because we're taking the product with the cube, somehow these variables are all independent. So what you have to do is, this is kind of a slight lie, because this system is not really going to preserve any closed set. It's going to kind of take it away. So basically, what you really need to do is you need to use these functions, but then you have to add some kind of reflection. Yes. So they generate an integrable system, but somehow you have to incorporate the reflection given by when you hit the boundary here, because otherwise it wouldn't preserve this cube, the Hamiltonian system that you get. So let's just say naively that you have this system with reflections. And then you can use the machinery of integrable systems to basically say, well, now you can actually find action angle coordinates and make this guy some kind of eye here that will project to Rn. So that this map here is the moment map of some toric action. So you kind of integrate, for those who know integrable systems, you know what I'm talking about. So you have to integrate these guys. And then the function I that you obtain is something like, I think it's 4, and then square root of 2. If you put t1 through tn, so you have square root of 2t1, and then square root of 2tn. So when you compose that, you get that the moment map image is just going to be 4 times norm of x1, norm of xn. So that's kind of the naive idea, is to use integrable systems in this way. But to actually tweak it so that it doesn't leave the cube, you have to somehow incorporate the reflections in a proper way. We use an idea of Benchy and Giannoni, which is basically how do you approximate a biliary trajectory? So to make the integrable systems argument rigorous, we use an idea of Benchy and Giannoni, which we actually learned in a paper of Marco and Peter Albers, which is to put a potential that is going to make the trajectory turn when you get close to the boundary. So you consider the system 1/2 of x1 squared plus epsilon over 1 minus y1 squared. And then 1/2 of xn squared plus epsilon over 1 minus y1 squared. So this yn squared. So this guy here basically means when you're getting to the boundary, you're going to have to, when you're getting to the boundary of this region, you have, this guy gets bigger and bigger, so you actually flip the other direction. So now this is still going to be an integrable system, and it's separable in terms that, it can do one variable at a time. So you basically end up with just a one-dimensional integrable system, and you can apply all the standard techniques to get a map that is similar to this I, but it's going to depend on epsilon. So it's not going to have such a beautiful moment map, but it's going to be something with a bunch of epsilons. And then we use some standard, again, symplectic geometry argument to say that they're going to kind of fill up the domain. And in the limit, we get that our whole symmetric domain times the cube, the interior of that, has a Hamiltonian toric action whose moment map image is exactly what we want. Okay? So that's the argument for this theorem. So I'm going to say that's basically it. So if you have any questions, you'd like to understand the argument better, you can ask me at the end. But now, I want to explain how we go now from knowing that these domains are toric domains to actually getting the rigidity result. So actually, this theorem is the kind of theorem that I said for the pessimists. So this is the kind of theorem where rigidity, where you have basically the strongest rigidity you could ask for, which is inclusion. So what do we use usually to get rigidity results? We use symplectic capacity. So we have to basically show that nothing better can do. So now the second part of the theorem is the rigidity result. So basically it's the following. So say that omega is the moment map image of one of these symmetric domains. So omega is a subset of the first 2 to the nth region in Rn. And it's symmetric, means, if you can flip it like this, and you can, you basically can flip it about all the coordinate axes, all of the planes like that. X1, xi equals xj. You reflected all of these. And then, and now we say that omega prime is either the triangle or the cube. So now I claim, so the theorem, or the claim, is that the toric domain x omega embeds into x omega prime if and only if omega is contained in omega prime. And also the other way around. So x omega prime embeds into x omega if and only if omega prime is contained in omega. Okay. So I said that I was going to use capacities. So what capacities do we use? Well, I used to work with ECH capacities, and I still do. They're very, very powerful. But we're doing something in higher dimensions. So the ECH capacities only work in dimension 4. So there are these other capacities which come from contact homology, if you're courageous, or if you want things to be rigorously defined as of 2017, you use positive S1 equivariant symplectic homology. So there are these capacities from what's called, it's a very long name, positive S1 equivariant symplectic capacities, also known as contact homology capacities, but so should be. They should come from contact homology once all the fundamental pillars are accomplished. But for now, Michael and Jean Gut wrote a very nice paper defining these capacities using capacities from symplectic homology, using S1 equivariant symplectic homology. So this was done by Jean Gut and Michael Hutchings. And the paper appeared on the archive less than a month ago, thankfully. Yeah, so the conjecture is that they're equal to Ecklenhofer. Yeah. So, so we can use these capacities. So what are these capacities? So say that we have a, let's just do a star-shaped. Let's say that X is a star-shaped domain in R2n. So they construct a sequence of capacities like that. And these CKs are all symplectic capacities. Not necessarily normalized, but they're not normalized except for C1. Okay? But they also, in their paper, they compute these capacities for the concave toric domains, which are the ones that we're interested in this talk. So they show that, so if you have a convex toric domain, x omega, so maybe I should draw the picture in 3D to convince you that I could be working in higher dimensions. So they show that, for example, C1 of x omega is going to be the smallest of these three numbers. So the smallest of the x intercepts. So if you call this, I don't know, A, B, and C, so C1 is going to be the minimum of A, B, and C. Okay? So you basically take the intersection of the domain with the with each of the coordinate axes, and you take the largest point there, and you take the minimum of all of these for all the from 1 to n. Okay? So in 2 dimensions, it would just be the smallest number between these 2 lengths here. But because we have a symmetric domain, in our case, they're all the same. So if omega is symmetric, in our sense, then C1 of x omega is the parameter A, which is this guy. So I can write this. This is a supremum of T such that T EI belongs to omega. Okay, that's the first capacity. And then they also prove a very interesting result in their paper, which is an asymptotic result. They prove that for a convex toric domain, x omega, they prove that the ck of x omega divided by k, as k goes to infinity, converges to what's called the cube capacity. So the cube capacity is the largest cube that you can embed. It's like the Gromov capacity, but instead of using a ball, you use a cube. So they proved that basically this cube capacity for a concave toric domain is exactly this number. It's the largest cube that can be included. So this is good Hutchings. And they proved that this guy, using this asymptotic result, they proved that this is equal to the largest cube that you can actually include. So this is the supremum of C so that P C C C C is contained in x omega. So P C C C C is a cube, is a polydisk. Okay. Okay, so just knowing this fact, C1, and C cube, we can actually finish the proof of the theorem. So let's do that. So I have my symmetric domain, and I want to embed it into a ball. And I have my symmetric domain, and I want to embed it into a cube. So let's see how to do that. So if I want to embed this guy into a ball, you see that what I need is the cube capacity. So the cube capacity is going to give me this point here, this length here. And the cube capacity of the ball is going to give me this length here. So if I make sure that this length is less than or equal to this length, which is necessary if I have the embedding, then that means that this guy has to be included in here. Okay, this uses the symmetry of the domain. So in this direction, we can use the cube capacities. So to go the other way, I want to embed this basically triangle into this region. So now what I use is I use C1. So C1 is going to give me this length, and C1 gives me this length. So if I know that this length is less than or equal to this length, then I can put it in here. Okay? So maybe it's hard to follow when I'm I'm constantly moving my hands. But basically, if you see what these guys are, then you can check that this is true. So in this case, if I'm trying to embed this symmetric region into this cube, you see that if I make sure that this length here is less than or equal to this length here, then it fits. So basically, I need C1. So C1 is going to give me that this length, if this embedding exists, then this length has to be less than this length, which means that it's actually going to fit. Okay, let me not keep these things in. And going the other way, now it's basically by definition, this guy is going to fit into here. That's the cube capacity. That's basically giving the definition of the cube capacity. What's the largest cube that fits in here? So if and only if, you can actually include it in here. Cube capacity. So you see that these capacities are giving all the sharp obstructions that we needed. I want to say a couple more things. One is that it's interesting that to embed the ball into this guy, we use C1, because that's equal to the Gromov capacity in this case, which is the biggest ball you can embed. And to embed the cube, what we need is the cube capacity. And it's also interesting that going the other way, you get some kind of dual. So you use kind of in some sense, I don't know in which sense, but in some sense, C1 is kind of the dual of C cube. It's some kind of C infinity. And here we use, it's also the dual. So I think it's an interesting fact. And I'm going to end with just telling you what we're trying to prove now. So I should say theorem in progress, because it's not really written yet, but we believe it's true, which is that if you take the three-dimensional ball times with the three-dimensional ball, that is symplectomorphic to a six-dimensional concave toric domain. So something like this. So it's kind of a generalization of my original result. And I should say that at this point, maybe you think, oh, that's great, everything is a toric domain, But I'll just warn you that it's probably not true. I mean, these are very specific cases where we can find an integrable system. So if you look at integrable billiards, for example, it's highly possible, it's likely that we'll be able to do a similar thing. So the next question is taking, say billiards on an ellipse. So you take ellipse times a disk. And we're pretty sure that that's going to be a toric domain too, although we haven't written it down yet. But if you take something else where you don't have integrable billiards for some reason, or most billiards are not integrable, then we have pretty much no clue of how to do anything related to embeddings, because it's probably not a toric domain. So the philosophy is that if you have some kind of integrable billiards, then you have an integrable system, which probably is a toric system, toric manifold. But if it's not, then we have no idea, and we would need new methods. All right, thank you.
Questions?